If we could just give him a round of applause.
Thanks for the introduction and the invitation, and I will make it short to keep you guys for lunch on time. So I think Thomas has really great introduction about the MR imaging and also using deep learning and other things for the reconstruction. So my role at Imperial College, we are focusing on the cardiac imaging. So I will be more focused on the cardiac imaging and how to use AI to improve, for example, the reconstruction and also analysis for the data. So as you can see here, I say AI for cardiovascular imaging here. I make a note here. It's called augmented intelligence. So I will explain to you why is that. And so firstly, I will give you an introduction. So I'm not quite sure about the background of you guys. So maybe some guys not from the computer science, or maybe some from the clinical studies. So normally I just give an introduction about the artificial intelligence. So we got so many different talks about artificial intelligence, for example, the narrow intelligence and also general intelligence and the super intelligence. So currently, unfortunately, we are still at the narrow intelligence stage. So normally we can only do a training a model, try to solve one single problem, and then train another model to do another one. And maybe the general intelligence is more similar to our human beings. We can learn play pianos, riding a bike, driving, and several things. So that's general intelligence, and also something called super intelligence. That's what I don't understand. So that's even beyond the human understanding. So we are still far away from these higher stages. And so the question is now we are at the narrow intelligence stage. Why is working so successfully? And I think there are 4 different reasons. So the first thing is about the big data. So we have got huge data. Even now at the hospital, we got loads of data that's labeled by the clinicians. So we can train the model efficiently. And the other thing is we can build really complicated models. Try to generate these models to explain the nonlinear properties of the data. And also we got the powerful computing. So I think today, this afternoon, there will be some talks from NVIDIA. So we got loads of powerful GPUs. And recently I submitted one proposal to the research council, and then after 6 months they told me, okay, your GPU is not up to date. So that's ridiculous. And also the other thing is about the the funding. So we got huge funding now for the both in the industry and also in the academia. So we can got lots of people working on this. Unfortunately, we lose people from the academia. Lots of people go to the industry. So as I focus on the healthcare, so I just give you a brief introduction about how AI can do in healthcare. We do a wearable device, smart watches, and to give the monitoring about the signal of our bodies. And also we can do computer-aided diagnosis using images acquired from the hospitals, and so many other things. So next thing is I want to give you a really brief introduction about deep learning in just 3 pages, no equations. So I think most of you people may have some basic knowledge about programming. So during we do programming, normally we just set a bunch of rules, and also we got lots of data, and we do traditional programming, and as we run it, we got the answers. So the deep learning is the same thing, but we just turn around the elements. So we got the answers, and we got the data, and we build up the algorithms, and we try to derive the rules from the data. So that's the thing about deep learning. So the final page, I just show you some really commonly used deep neural networks architectures, when we got simple data, we can use these artificial neural networks, and if we got images because they are too large, so in order to make it more efficient, we try to use the CNNs. But we should always remember the convolutional neural network artificial intelligence is not similar to our brains, because just for example, for our human brains, if we try to simulate one, we need a computing power about 6 of them. That's a huge amount of power. But today, in the morning, I just have some surreal. I can still be here and do the presentation. So our brain is much, much more efficient. So that's why I think maybe some research have been done in the DeepMind. They are very, very important, because they try to find the basic science about neuroscience, how our brain is working. And so just make a brief summary here. So we just try to use the huge data to overfit the model. So our AI is actually not artificial intelligence, it's just augmented intelligence using like a big data. And now I will show you some like a showcase for the applications in the cardiovascular imaging, like recently what I have done for the like clinical applications. So I choose these like 4 different projects. So the first one is the whole heart segmentation. So what we have done is we collect the data from the hospital for both the CT and the MRI images. We got over 100 data sets that were all labeled by the clinicians. And then we published the data actually and online, and we invited people to submit their algorithms, try to segment these different architectures of the heart. So currently it's still online, so you guys, if you're interested, you can log onto our website and download the data and also train your algorithm to do it. And based on the anatomy we segment from the heart, we're also looking at one particular clinical questions about how we can quantify the scars on the heart for the atrial fibrillation patients. So the things we need to do is firstly, we try to segment the left atrium. So as you can see here, that's the that's the ground truth we got from the clinicians, and that's the result we got using our deep learning-based methods, and also we do some semi-automatic modification for the deep learning-based methods. So we got better pulmonary veins to be segmented. And the third project is quite interesting. That's recently published by the radiology paper. So before, when we try to see the enhancement of the fibrosis on the heart, normally we give some injections for the patients and wait about 5 to 10 minutes and then we do this MR scan. And however, some people, for example, got some kidney problems. They cannot given this kind of enhancements. So we try to use something called motion analysis for detecting this kind of abnormality. So the assumption is that even before the patients got this kind of fibrosis, they may have some physical changes of their heart. So there are already some abnormalities of their motion. So we acquire both data sets for something called scene images. That's just like a data acquired for the whole cardiac cycle to detect the emotion. And also we acquire data for called late gad, which we give the injection and then do the scanning. So we find a correlation between the scene images and the late gads, and we find the motion abnormality correlates with this enhancement for the fibrosis. So maybe in the future we don't need such an injection of these contrasts. We can just acquire the scene images and then we get the motion abnormality detected and then find the fibrosis. And Project 4 is super resolution for the cardiac images, so I will introduce you more details later. And actually, this is one interesting picture I took from the MICAI 2018 conference, which is one of the top conference in medical image analysis. As we can see here, the keywords we can read it is image segmentation using deep learning. You can read it. Sounds like it. So as you can see here, the segmentation is still a major problem for the clinical field. Lots of people, they try to solve this using deep learning or other machine learning algorithms. So as we at Brompton Hospital, we also look at these projects, I already introduced you about the whole heart segmentation and also left atrium segmentation, and also we applied for the scar segmentation, which we try to find the abnormality on the heart. So this is the online challenge we organized in 2017, but now it's still ongoing. So we have got about 30 participants all over the world, and we do the ranking for different algorithms, and the results are pretty good. So we can see here for example, for the left ventricle, we got a segmentation accuracy already over the 90%, and some of the arteries or some other substructures like atrium, we got lower accuracy, so we can still try to improve it. And for the scar segmentation, we also designed some really complicated architecture for doing this. The reason is we designed these 3 different networks to resolve the delineation for the cardiac anatomy and also for the scar. So the first network I want to introduce you here is called sequential learning network. So the thing is, we try to mimic the daily routine clinician doing. So normally clinicians, they will not look at the 3D images because it's too hard to understand. So what they do is they load the 3D images and then they just scrutinize it slice by slice, and then they try to find the correlations above the slice or below the slice. So what we try to do is we try to use these recurrent neural networks, try to resolve the connections in between these slices. So that's why we designed this sequential learning network. And also for the scar, they are discrete small regions on the heart. So we try to also incorporate these attention neural networks to force the network to focus on these small regions and try to extract the small regions of the scars. So by combining all these different architectures, we got pretty good results for both the left atrium segmentation and the scar segmentation. And also we can see the visualization on the right-hand side. So the green region are the segmentation results from our automated algorithms. And also we can compare with the electrophysiology studies because they try to measure the voltage map from the cardiac, so which means the low voltage corresponding to the abnormalities. We can see sort of correlations between. However, for the EP studies, the resolution of them is quite low, so we couldn't correlate properly quantitatively with the MRI. So we can also further doing some more works for that. So I talk lots about the segmentation, and currently my research is actually interesting in the reconstruction of the data. So the reason why I'm interested in that because I believe the data quality is much more important than the data quantity. So there are lots of people, they try to design really, really complicated function F using deep neural networks. However, they just ignore the fact that the input data is rubbish. So they always get some rubbish out. So that's why I'm trying to do is I try to resolve the problem by just get a really good quality of the inputs, and maybe we don't need such a really complicated function F here to do to get a good results. So this kind of problem, I summarize it as solving some inverse problem that's including the reconstruction and super resolution, and also in general we call it image quality transfer, including the denoising, image impeding, motion correction, and etc. So they can all model in some general framework to do that. And this is one of the I still almost forgot about the topic of this workshop. It's about the GAN. I will talk about the GAN work. So the GAN work we have done is for example, for the super resolution work. I believe you guys already know the background about the GAN, but I just give you a simple introduction. So the GAN includes a generator and discriminator. For the generator, we normally got a encoding and decoding part, so you can use some sort of UNet or ResNet based architecture. And the discriminator normally a CNN, they just do some classification of the generated result with the ground truth. So by doing these, competing with each other, we can get a good result for synthesized images. So we apply it to the cardiac images, because normally for the cardiac images, they got really low resolution, etc. However, as we know, for the GAN-based methods, normally we got unstable training and sometimes collapse modes problems. So what we try to do here is we try to improve the efficiency of the GAN. So how to do that? We try to make a GAN focus on the RIs of the for example, in this case, it's the myocardium region. So that's the only region we are interested in. So we just crop it out to add an additional detection layer to that. So we will not get any contamination from other structures. Here, maybe you can see some structures from the lung. We are not interested in. We don't want to synthesize any these artifacts into our myocardium quantification. So that's the basic idea of this method. And also we also try to improve the performance of GAN using the method already being mentioned by the other speaker. We use the multi-scale based discriminator to improve the performance of the GAN. And the other work I we have done using the GAN is called Dagger Methods. That's one of the first methods for using the GAN to do the MRI reconstruction. So the architecture is quite similar to what people you may see from the super resolution work. So we got the generator here, we got the pixel loss, and also we do the loss in the frequency domain, in the K-space domain, and also we try to improve the perceptual loss by using this VGG network, and also following by the normal discriminator. And that's the total cost function of our model, and that's some simulation result using neuroimaging. We can get pretty good results. And also we use this trained model to test with the cardiac images. It still work quite good. And recently we also try to apply this deep learning or GAN-based method for the diffusion tensor images for the cardiac. And at Brompton Hospital, we are currently focused on the diffusion tensor imaging because we try to see how the fibers in the heart, the direction of the fibers goes in the heart. For example, if you got some fibrosis, maybe these fibers will be damaged. So that's why we try to use diffusion tensor imaging to see the abnormalities. However, for the diffusion image, we try to resolve the fiber directions. We need at least 6 scans to solve the eigensystem equations. So that's why the diffusion tensor imaging is extremely slow. So currently you can see here that's some ex vivo studies, but in vivo studies we can only do a 2D slice. Even for one 2D slice, we may require 15 minutes to 20 minutes to finish. So that's not feasible for the patients. So we try to speed it up, and also we try to do multi-slice diffusion tensor imaging for the heart, and we can see a full picture in 3D for the abnormalities. So that's the reason we try to apply this technology to this. And here are some initial simulation work we got. So on the left-hand side, that's the super resolution we have done. So as we can see, compare with, for example, the bilinear interpolation, that's obviously quite over smooth. Our GAN-based method is much clearer. And also compared to, for example, method like SR GAN, our method reduced quite a lot of the artifacts, maybe synthesized from other organs that not belongs to the heart. And on the right-hand side, we also apply similar technology to the cardiac diffusion tensor imaging reconstruction. And we compare with the zero filling method, which is similar to the bilinear interpolation in the image space, actually. So we reduce the over-smoothing problem. And our method got similar performance with the dictionary learning-based method, but our method is much, much faster. It's about a few milliseconds to finish the reconstruction, but for the dictionary learning, it may be hours to finish. And also, by tuning different parameters of the model, we can also get the uncertainty for the reconstruction. So maybe currently we are thinking about how to use this uncertainty. Maybe we can use it like an active learning model. We tell the clinicians, okay, these regions, they are not reconstructed accurately. Maybe we need to tune the model again and then produce further results. And I just want to make a short note about the reconstruction work we have done for the reconstruction of the MR. Currently, it's simulation-based. So we can, for example, downsample the case-based data for 5 folds or 10 folds and then get good reconstruction. But in real case, we couldn't do such a acceleration factor because normally patients go to a preparation for scanning and lots of other scans before this scanning. So the reason is we couldn't get such an acceleration factor. And that's all about I'm going to talk. So thanks for my colleagues at Imperial College and Brompton Hospital, and our current study is funded by the British Heart Foundation. All right, thank you.